Good afternoon. Okay, everybody is ready to go. Uh, so this is our last but not least. This is our last session. Yes. Pooja was asking me how the 50% milk fat solution friction factor is. No, the question is how the 100% milk fat solution is less friction factor than the.
You said that if the fat content is more, then there is more lubrication, so the friction is less. So if the fat content is more in 80%, then how the friction is like higher than the 50% fat? That's what I'm asking.
Okay, primarily because that's how they try to mimic that. They added some ingredient into the 50% fat. The idea here is it's not just a friction factor number, but how the consumers um, how the consumer favorably look at this 50% milk fat solution, and that's how they developed this 50% milk fat solution. So the consumers prefer the 50% milk fat solutions compared to 80% and 100% solution. Even though the 50% milk fat solution is higher friction factor than the 100% milk fat solution. Why it is like that? If you just look at the pure fat content in the milk, then these numbers may not make sense. But it's not just a fat content only, but the ingredients they put in the 50% fat favored by the consumers, even though it has only 50% fat. Correct. They added other ingredients, proprietary ingredients, which we don't know what they put it in, to substitute for the fat or flavor compounds. So consumers like the 50% fat, and that is the idea behind creating 50% fat solution, so that the consumers will still like it and then they get a better product. Does it make sense? Yep, that's what it is. So, yeah, very good point. So it's not purely about the amount of fat in the product, but it's also that how they were able to mimic it so that consumers favorably looked at it. Make sense? Yep. Other questions? So now I'd like to spend some time with you. Final push in terms of the texture and rheology. So what are the new things happening in the last 10-15 years, or what are the new opportunities available so that we all can do better job of measuring these properties using the additional resources. So let's go back to our original thought. What's the texture and rheology? As we know, food texture is defined as all the rheological, mechanical and structural attributes that perceptible by the means of mechanical, tactile and where appropriate visual, auditory receptors. So these textural attributes of foods can be effectively measured with various advanced techniques such as texture analyzer, but again and also rheometers. And then rheology, the science of deformation and flow of matter. So rheological characteristics are measured by the various advanced techniques like dynamic mechanical analyzer, NMR, MRI and stuff like that. So why we have to do? Because advanced rheology and texture is very important, because they give a strong relationship between the properties, structure and processing of the food material. They can help to describe the mechanical structural behavior of the food materials as a function of stress, strain, temperature, pressure simultaneously in order to develop materials. with the correct processing behavior based on the viscosity, elasticity and time. And these parameters give deformations and flow behaviors of different solid and liquid using dynamic mechanical testing method at melt temperature or even elevated temperatures. So, the principle of functioning principle of advanced structural rheology is a measuring force as a function of time or distance as a probe fitted to a textural analyzer deforms a sample in either compression or tension. The probe is moved at a defined speed in either up or down or more commonly down direction, and the resisting force is measured throughout the test. So, this is the guiding principle in terms of in general texture and rheological measurement. So, when you look at the rheological methods, when you look at the liquid or semi-liquid foods, they are mostly based on the analysis of the viscous Newtonian fluid, non-Newtonian fluid, that is what we looked at it so far. Whereas rheological methods for solid foods deals with the relationship between the strain, stress and time. And the strain refers to the material deformation, whereas the stress is an applied force due to difference in cross-sectional area also. So far we also looked at the texture profile analysis. There is lot of ways you can test these food materials. And classical example we did was texture profile analysis, double bite. So from that, what more we can do with this method? So this is what we looked at it in terms of texture profile analysis. So we get a lot more information here compared to just a hardness only, but this allows us the differentiate between different samples, and also people tend to correlate this with the sensory analysis. Different profile, different characteristics we can measure, we can calculate, and that can be correlated with the sensory analysis. So what are the advanced rheological analysis? Typically, when the rheometer is coupled with the nuclear magnetic resonance, magnetic MRI, magnetic resonance imaging, atomic force microscopy, confocal scanning laser microscopy, small angle neutron scattering, diffusing wave spectroscopies. So these are all the opportunities available. If there is a way they can couple the rheometer with this new way of looking at things, then we can take these rheological measurements to the next level. So that kind of opportunity is available there, but lot more work needs to be done in that area. Right now, there is no other, there is no work going on in this area, but still a lot of room for that. Basically, they need to couple rheometer with this newer technology, so that they will get a lot more information about the products, and that will help the industry to develop new products. And also the, I meant to say currently there is a lot of things going on in this area. They are coupling, rheometer is coupled with these technologies, so they can really provide a lot more advanced information, which will enable us to understand a lot more about the complex analysis of complex food material. We know that food materials are very complex. They are not like polymers. They are viscoelastic. So these kind of coupled technologies will help us out to understand a lot more about the material itself, and it will help us to further enhance our understanding of the this material. And these are some of the opportunities available: microscopy, spectroscopy, small angle X-ray scattering, small angle neutron scattering, or magnetic resonance equipment. So these technologies can be right now it can be coupled with rheometer, so that we can understand a lot more. Because currently what we are doing is we are doing rheology testing, we are getting the information, and we are trying to correlate with the structure, microstructure, and that is not effectively happening now. we are doing microstructure, we are doing rheological testing, and we are trying to match the information. There is no clear understanding of connecting my rheometer results with the microscopy work. So that area needs to be further explored, which is not happening now. So there's a lot more opportunity there. Another area is currently tripology is looking at the chest by itself, but if you can couple that with the QCMD, which is quartz crystal microbalance with the dissipation monitoring, and they may add a fundamental understanding of the adsorbed layers of protein and boost the design of a new ingredient formulation for use in low fat, high protein food development. Okay, that is the area everybody is looking at it, and there is a lot more room for improvement. So we will see a lot more research work, new way of thinking, more product development once they are able to couple typology with the QCMD, which has a lot more potential. So there are more to come in terms of the additional research work and new product development. And currently, in my opinion, the challenge remain in correlating microscale rheological behavior to macroscale rheological attributes of food material. So we do microscale studies like rheometer and things like that, but in reality, all the food materials go through macroscopic attributes, right? Because when we do the actually sensory analysis and all, everything is macroscopic. Nothing is micro scale level, but we do micro scale analysis. So that needs to be further explored, so that whatever we are whatever way we are consumers are doing the analysis, we should be able to correlate the micro scale rheological behavior to the macro scale rheological attributes of the food material. That needs to be further explored. Currently, those kind of things are not happening. We are just doing the rheological thing micro scale, and then there's separately the sensory analysis doing the macro scale rheological attributes. So they are not connecting now. So that needs to be further explored, in my opinion. So I am going to show you some of the measurement techniques. So for the past decade or 10-15 years, there has been growing interest in various advanced techniques, instruments to provide in-depth investigation of food behavior under various conditions. The recent advancements of food rheology texture are as follows: ultrasound technology. So there's a lot of things happening with ultrasound technology, and then getting information in terms of the rheological behavior. And another area is the large amplitude oscillatory shear and Fourier transform, because whenever we do rheological testing, we typically do small amplitude oscillatory shear, micro scale, but there is a lot of room for the large amplitude oscillatory shear test. That I am going to talk about it in next few minutes. And also NMR, nuclear magnetic resonance, dynamic mechanical analyzer, DGA, and differential scanning calorimeter. So these are things happening now, but lot more needs to be done in this area. Let's look at the large amplitude oscillatory shear and Fourier transform rheology. So what you see here is the stress as a function of shear rate. So it's a stress response for the shear rate you apply for the whole period of oscillations. You start in the middle of the oscillations, and for the viscoelastic material, the nonlinear regime, the shape of the loop deforms from its original ellipsoidal shape due to the deformation of the stress output signal. So this is what you get in terms of the large amplitude oscillatory shear for any food material. So this is a typical output you get when you do the non-linear rheological analysis compared to linear viscoelastic region. So more needs to be done in this area, and from this type of test, you tend to correlate with the actually what's happening in the non-linear viscoelastic region. Any questions on this type of test? This is a totally new area of research. People started doing in this area of research, and they are trying to correlate with the sensory analysis also. Because previously, when they do the small amplitude oscillator shear, that's just a primarily looking at the material behavior, not so much about the macroscopic scale analysis. So there's a lot of room for improvement here. Yes, Rubati.
The parameters that we have to fix for this kind of test, like for example, if it is, we have to keep a particular strain and check the stress like that.
That is true, yeah. And also you do the same thing like a frequency sweep, and then a stress sweep and stuff like that. But whatever you do small amplitude shear, here we are looking at a higher large amplitude oscillator shear. Previously, thought process was because we are looking at the micro scale analysis, what is happening micro scale level. So that way we are trying to understand what's happening without damaging the sample. Now in the large scale, large amplitude oscillator shear, we are damaging the sample, but that's okay. That's what happening in actual sensory analysis, right? So we feel that this way you can correlation is better. Yes.
The main purpose of doing this experiment only the deformation, measurement of deformation only.
Measurement of you do deformation, strain, and then you follow the response, stress response, right?
So the deformation when we see in the lab, it is in two directions. First it deforms, then second. In this process, how much?
Okay, I think what you saw in the lab was purely compression test, right?
Yes, the first bite and the second bite.
Correct. So that is the texture puff analysis.
It was the total what we do in our mouth.
Correct. So that is compression test. This is oscillation test, where you put the sample, you have the sample, and then you apply the oscillatory shear. So you apply the strain, oscillatory shear rate, strain, and then you measure the stress, and that's what happening in this test.
The different colors comes while
Okay, different colors comes primarily because you are you initially it's a episoidal shape. You start in the center and slowly you keep increasing the strain, and then you are measuring measuring the stress response. So this is where your starting point. Middle point is starting point. So you start with this ellipsoidal shape, and it's slowly going into it is slowly expanding, and then you're going into the higher strain rate. You use the rheometer for this type of test. Exactly, yeah. So that's why it's a sinusoidal oscillatory strain. So that's why it's going from positive to negative. I think in the lab the mayonnaise you did only for the viscosity measurement. They didn't do the oscillatory test. Exactly, yeah. Any other questions?
So what? Suppose we did this experiment and we got this beautiful graph, and in our suppose writing the literature, so if we just put the table and just omit this graph, so how is that goes? That should we be paper should be more browsing with the more of the pictures, or the tables also do that content?
Okay, the question here is this graph only be sufficient to describe the process, or we need to add a table to describe the process? In general, pictures speak for 1,000 words compared to tables. So if you really convert this all the data you see here into table, it will be a lot of table where people will not be able to follow the whole trend what's happening. So in this case, mostly it is better to put them in the figure than putting it in the table. It is similar to what you do with the small amplitude oscillatory test. You typically present the figure only, not in the table. Maybe I can explain to you a little more if I show you a result. So these are all the dynamic rheology test these authors did, and then you see that G prime and G double prime as a function of strain. So it's in log scale. So if you present these graphs, this data in a table format, it's difficult to explain the whole process, what's happening. What they have done in this work is they have collected this data for their gels they developed, and then they calculated a term called flow transition index, which is a ratio of the strain at crossover point divided by the strain at the end of linear viscoelastic regime. That's what LVR means. So if you look at going back to the data what they collected, so if you take this sample, so the crossover point is here, and then their LVR value is somewhere here. Okay, so this is about 120 something, 120 kilopascal, and then LVR is around 10 or 12 kilopascal. So 120 divided by 12 are so PPI, so 158.29, and then this LVR is 7.36. So they get the flow transition index of 21.5. So it's easy for them to explain that process, what they collected, and then they are discussing about the flow behavior index numbers and how they are different for different treatments. So in this case, they are providing the graphs, pictures, figures, and also they are coming up with the calculations and shows what they collected and what is the importance of this data. So if there is a way, I mean, if this is a way you can do that, so that the readers, the reviewers can really understand what's going on, and then if you convince them this is the way they did, and they also discussed about the results in a very elegant manner, so it's easy to get published. So that is what I would do if I'm doing this kind of research work. So important that you put the figures, because if you put all the data, all these figures in a table format, there will be a lot of data, and they cannot even understand what's going on. But looking at the figures, it's much easier to understand. So moving on, NMR, nuclear magnetic resonance imaging, is used to investigate the rheological characterization of micro, nano, or multiple emulsion of food samples for further investigation. This technique of rheological measurement enables food manufacturers to design foods in a new fashion, which leads to improvement in the products. So this is the NMR instrument setup. The liquid food samples are placed into the NMR tubes. You see there are two tubes here with acetone and perform rheological measurements. And these are all the tangential profiles, velocity profiles for the flow of different material types with the inner and outer cylinder radii R1 R2. So, this leads to the various tangential velocity profiles depending on fluid rheological behavior. So, they looked at the NMR and then they can see that Newtonian fluid behavior is straightforward here, and then you have shear thinning and also shear banding, yield stress force with the shear banding, and also simple yield stress fluid is over here. So, this is where they are trying to correlate the rheological behavior by using the nuclear magnetic resonance imaging. So, this is new way of thinking and looking at the fluid flow profiles, and that helps them to understand what is happening with the material itself. You all know the dynamic mechanical analyzer. We use it a lot of times for this is a non-destructive analytical method used to determine the viscoelastic properties of wood without altering the material structure, similar to rheometer. The sinusoidal oscillating stress or strain with the frequencies applied to the material, similar to a rheometer, and the phase difference between the oscillating stress and strain as well as amplitude ratio are measured. So, what you see here is both the storage modulus which is here in the blue color, and then the loss modulus is here. So, this is the crossover point. So, we can probably get the similar kind of results what I showed you in the paper, and it is a function of temperature here, and this is the phase angle. Phase angle is shown here as a function of the temperature. So, if you look at the phase angle, it can go up to 68 degrees. So, what it means is it is closer to more of a liquid than the elastic nature, because at higher temperature it gets softened, so it became more liquid, but initially it is less than 10. So, it is a more elastic material at low temperature. At a higher temperature it shows the viscous nature. The next one is the differential scanning calorimeter and also thermogravimetric analysis. Even though as name implies it is a heat flow, again it is a flow and deformation. So, they are trying to correlate these kind of results with the rheological behavior. So, these are a series of techniques that provide physical property measurement as a function of temperature, time and other variables. These two instruments heavily used in the characterization of food material. This is the function of temperature and the heat flow. So, you get two crystallization peaks, endothermic are seen here within this 100 to 170 degrees C temperature. When we talked about viscosity, we looked at only the time independent behavior. Time independent behavior of food materials. We have looked at the Newtonian and non-Newtonian fluid. We did not have a chance to look through the time dependent behavior of the materials. So, in time dependent behavior of the material, what we do is we measure the viscosity as a function of the time at a given shear rate. At a given shear rate, you keep measuring the stress value as a function of time. So, when you get this stress and the shear rate, then you get the viscosity. So, this is viscosity with respect to time. So, one is thixotropic, the other one is a rheopectic. See, if the viscosity decreases with the time, it is called thixotropic. If the viscosity increases with the time, it is called rheopectic. Lot of times these data may not be linear as it is, but most of the time it is a linear behavior only. Again, this is a test for looking at how the food material will behave in terms of if they are either time dependent or time independent. But in real life, we do not worry about time dependent behavior. right? Because if you have a product, fluid is there. If you want to measure the viscosity, we just measure the viscosity, because we don't need to look at how they behave with respect to time. So that's what lot of research work may not have. A lot of research work don't look at the time dependent behavior. Typically, they do only time independent behavior. And the new technologies, you all know that there is a lot of new sensors that's coming, electronic sensors, electronic nose. I got a chance to look through the YouTubes, and then I came across one electronic tongue. There is an instrument people are developing in terms of the electronic tongue. So I thought it would be nice to show it to you, so you can have some appreciation for the So basically, the way they measure these things is, you have the fluid, whatever you want to test the viscosity, test their time dependent behavior. So you have the fluid, you put it in the some type of viscometer, and then you shear the sample at a constant shear rate. Then you monitor the shear stress with respect to time. So shear stress over shear rate gives you viscosity. So you plotting the viscosity with respect to time. So it is not the yield stress at all. It is just viscosity at 0 point, and then follow the behavior.
We all know that we have 5 senses. We can see, we can hear, we can touch, we can smell, and we can taste. Now this is something that from very early on people have been trying to mimic by technical devices, which would do the similar job as we do. So we have dramatically sensitive optical sensors, we have very, very sensitive microphones. But when it comes to smell and taste, there's nearly nothing on the technical side that we can do. Now, why is that so? First of all, what is smelling and how do we smell and taste? This is a very complicated process where small molecules that reach our nose by air are then recognized by molecules in our nose and are then translated into an electrical signal that is transmitted to our brain and processed there, and eventually gives us the impression of we smell something sweet, we smell something like chocolate, we smell something like whatever. It is much more complicated than when it comes to seeing, because when we have a camera, then we have a device that translates photons into an electrical signal, and eventually we generate a picture, and we can even do this in color. Now when it comes to smelling, we talk about not photons, we talk about molecules. We have in some cases a single small molecule that gives us the impression of smelling, for example, mushroom, when we open a bottle of red wine, and it has then what we call the bouquet. It has hundreds, if not thousands, of small molecules that make then the richness of this full-bodied wine. And this is why then technically we have a totally different challenge, because we need to develop devices that can do the same kind of selectivity, the same kind of bandwidth, and the same kind of sensitivity. And this is why it's still not on the market as a smell sensor or a taste sensor in the way we have extremely sensitive cameras or photodetectors.
What makes this process so difficult to realize is the merging between biology and electronics. This is what we call bioelectronics. So essentially we want to convert a biological signal into an electronic one, just like our brain does. The way we realize our sensor is by taking from the world of electronics the concept of a field effect transistor. Upon normal operation, we create a stable baseline that is basically just the current between source and drain. Upon proper functionalization of this FET, we create a system that generates a selective electronic response to a given analyte by changing the charge transport characteristics of the graphene itself. And this generates an electronic readout. This is actually the major advantage of the system, to be able to electronically detect a label-free small molecule.
A key challenge in realizing this biosensor is the designing of the individual material's components. The material that connects the two electrodes, drain and source, needs to fulfill several criteria. First of all, it needs to be a semiconductor with excellent charge transport properties. It also needs to be thin and flexible, yet strong and robust as it operates in an aqueous environment. And it needs to be biocompatible, yet it must not interfere with the analytes in solution. Our approach to this project is to implement the world's thinnest material, graphene. We take this graphene and deposit ultra-thin layers of a metal oxide on the surface to create a hybrid material, and then tune the electronic communication between the two components by engineering defects and interfaces.
Once we have our graphene layer, we need to attach relatively large biomolecules onto the surface. And this process needs to be done in such a way that the biomolecule itself stays intact. And most importantly, also that the recognition of the analyte is still possible. So the orientation of the biomolecule really matters. Considering the plethora of functional groups inside a biomolecule, it's actually impossible to do that by using traditional synthetic chemistry. So therefore, we use a concept called bioorthogonal click chemistry, a chemistry that makes use of specific artificial functional groups that selectively and rapidly react with each other, but do not interfere with the functional groups of the biomolecule. You could literally say that this chemistry is orthogonal to biology or life, which is why such reactions can even be carried out in living systems. To understand and also to develop new bioorthogonal tools, we start by investigating those click reactions using computational methods. Based on these results, we select the most promising bioorthogonal reagents, which will then be prepared here in the lab. And after that, to finally investigate parameters such as selectivity, stability, and reactivity, we use optical methods such as fluorescence measurements and spectroscopy.
Like in an assembly line, the fabrication of our final biosensor requires different steps. Once the graphene is placed on the chip, the immobilization of the biomolecules can begin. Together with the Interactive Media Systems group at the TU Wien, we have created a virtual reality simulation for our students to illustrate the different length scales that we work with. At first, we are standing on a sheet of graphene, which is 1 square kilometer big, and every black dot is 1 carbon atom. In comparison, the biomarkers are huge. They are about 4 nanometers in diameter, which at this scale is the size of a small kid. The big yellow walls on the horizon are our gold electrodes. At this scale, they are 200 meters high. We don't just have one of these electrode pairs, but we have 100 on a single chip. Once the biofunctionalization is finished, the chip is transferred to our flow cell and hooked up to our electrical readout system, and the sensing can begin.
Just imagine you open your fridge, you see there is still a steak, it looks good, and then what you do, you smell at it. This is the final quality control for food, and this is what we would like to do also with a technical device. Environmental monitoring is something that we are extremely interested in also doing automatically with the network of sensors that monitors our environment. And last but certainly not least is all the medical applications. If we could develop sensors that smell what we have in our exhaled breath, what we have in our emission from our body, and we could sense that as a means to detect, is that a healthy person, is that a person that is under stress, is that a person that has a certain disease, that could be an enormous potential for applications as well.
The goal is actually to combine and miniaturize our entire sensor setup to something like this. This is our so-called dollar sensor, which we have developed with Professor Kimis's group from Columbia University. It's very cheap, it's lightweight, and it's easy to use. You just put it in and plug it into a USB port and hook it up to your smartphone, and it automatically starts with the measurements. The huge improvement of our current system is that by using specific biomarkers, we can make our sensor much more powerful and versatile. There are many challenges ahead of us, but the goal and the applications are worth all the efforts.
They are developing something which can be used for a lot of places, a lot of applications can be employed for this type of biosensors. I think that is the, yes sir.
Do you know them, or are you willing to collaborate with them?
No, I do not know them. I just picked up this in the YouTube. I would be interested in talking to them when I go back. So, but these kind of videos is primarily for the promotional material, where they try to talk about a lot of big thing. Only when you go closer to them, you will find out what exactly is going on. So, with a grain of salt, we have to approach them. But it's a cutting edge work, you know, when you think about that, what goes in and how many people get involved and what kind of things they are trying to do. So, it's fascinating for me. So, because because I'm not directly involved in this type of research, so it's a fascinating for me. So, hopefully we'll get a lot more new ideas, new technologies coming up, and it will be a great thing.
So how do you differentiate the smell and the taste? How we have sweet, sour, and
They didn't tell anything about that, right? They are talking about only technology of that.
they put four color of jars. How they measure why it is sweet or sour or salty.
Yeah, that they didn't even mention about that. These are all the opportunities available for them to do, but time will tell how far they can go, you know.
In the last one, at the end they were just putting some air with the mouth, and then started. What would be there? Those markers which they have coded.
Yeah. So basically, they are trying to characterize the breath, what they are getting. So they think that this kind of things can be employed in food also, application of food also. So for example, if you are smelling the meat, you can see that whether it is a fresh meat or it's a stale meat or something like that. So that's what they are trying to do when I looked at the video here. So any other questions? Okay, this is all about mathematical modeling. We talked about power law model before. There are a lot more models available, not just only power law model. One of the other model is Kaysen model. This is structure based model, and usually they use it for the characterizing the number of fluid food suspensions. So I'm going to, after I wrap up this presentation, I will show you some other information from the e-books you are going to get tomorrow when you get your flash drive, so that you can see what kind of information you can get from those reference materials. So what are the benefits of advanced rheology and texture measuring technique? They are promising tool for understanding factors that influence the food rheology and texture, because the way in which the food deforms, fractures, flows and breaks down is a key component of textural sensations, and they offer a significant relationship between food rheological behaviors and sensory texture attributes. And also these measuring techniques are relatively straightforward in food system, and they provide opportunities to research the concepts and theories related to food and biological sciences industry. Some of the challenges of advanced rheology and food measuring devices techniques. Advanced measuring techniques cannot completely replicate the overall conditions and changes to foods during measurement. Only we can try to correlate as much as possible, but we are not trying to completely replicate. Only so much instruments can do, but overall sensory way of the sensory way of evaluating food material is lot more complex, and that cannot be replaced with the instrument techniques. So fundamental rheological tests are limited to samples that are homogeneous and isotropic, but foods that contain large particles separate rapidly or have anisotropic structures are difficult to analyze accurately using advanced techniques. Because if a food is a viscoelastic material, it's not purely elastic, cannot be elastic. So food is much more complex than what we think it is. The rheological tests using advanced techniques can at best measure a few properties of food at a time, whereas descriptive analysis panelists can measure more textural attributes in a single food simultaneously. Thus, multiple rheological analyses are needed to collect sufficient information to predict texture or rheology of the food sample. Time will tell when we were able to do that. I think more and more we go towards the correlative, the sensory analysis. It looks to me that they are going to predict much more than the instruments can predict down the road, because biosensors are really coming up very well. So they will be doing a lot more predictions, lot more measuring of actually what is happening in the food. Challenges in food rheology, mostly the rheological measurement, surface of wall sleepiness, it's a big issue still. The sleep characteristics of wall may significantly dominate the perceived behavior of the food rheology. However, to characterize and understand the nature of wall surface sleepiness is challenging. Interfacial rheology and its implication of food structure. The foods are typically full of interface and contain variety of surface tractive materials which contribute to microstructure formation. To optimize the microstructure formation to analyze food rheology, it needs to be a complex configuration in three-dimensional shape, which is complicated. At best we can do 2D, but three-dimensional spaces which is complicated also. Lastly, rheology education in food science beyond 1D rheology need to be occurring. So a lot of undergraduate courses in food science or food engineering often include some basics of rheology. These are however often limited to the discussion of shear flows, avoiding the vector and tensor analysis. Even looking at the shear flows is also, it's not an easy thing, right? It's a very complex process, and the theory is also very complex, so it's going to be challenging. Any questions anybody has? Some of the future sessions, The research focused on understanding the food texture should also include microstructure analysis. I think that's what I said before. Many studies measured food rheological and sensory behavior but not microstructural features. However, they are critical to the fundamental understanding of the food oral processing behavior. And also the rheological analysis should have specific pathways of food breakdown during applying and best practices for characterization and incorporation during testing while still gaining fundamental information are needed. So, this concludes our discussion for this afternoon. I am going to show you the e-books I told you about, and I am going to show you some of the pages there so that I can explain to you what more information you can obtain from these references. These are the different models has been used in the literature, including power law model and the Gassen model. So, this may be a good source of information for you down the road when you try to develop your own materials, where if you need to model them, you can use some of the models to check it out as a starting point. Again, this is we already talked about it, time independent fluids, viscosity with respect to shear rate. So, you can see that there is a Newtonian behavior, constant viscosity, shear thinning is decreasing viscosity, shear thickness is increasing viscosity, and then the Herschel-Berkeley and the Bincombe plastic materials will have a yield stress, and then the viscosity decreases with respect to shear rate. Okay, this part of the book describes the inline viscometer. We have looked at only the capillative viscometer, Brookfield viscometer, and rotational viscometers. But this is inline viscometer, which is very much needed in the industry, and this has been in the industry for a long time. What it is basically they connect the viscometer to the product inline, so that they can measure the viscosity of fluid going through the pipeline, and then based upon that they can also change their product line, and then that way they can improve the product development work, and that's the idea behind using the inline viscometer. Okay, it's interesting. I just want to show you this one because not all the texture profile analysis are done very standardized method. There are ways people define them differently and use them differently also. For example, if you look at this springiness, all along we have been saying that springiness is length 2 over length 1. This author, they thought springiness is only L2, how much it is springing back. So, what is the deformation in the second compression, and that's what they are thinking. I mean that's how they are describing the springiness. And also there is a definition of stringiness. Stringiness is when the material stick to the teeth, and then how much time it take to release it down, and they use this as a stringiness. So, there are different ways you can describe the same thing, but it's just a matter of defining them ahead of time and then following characterizing your food material. So, what you see here is the modulus value, and I think I showed you before also, but this is the schematic of that. Strain or stress you can get in a linear viscoelastic region. So, basically you do the strain sweep or stress sweep depending upon the instrument, and from that you can find out the linear viscoelastic region, and then you fix this stress value or strain value, and you do the frequency sweep or stress. This is stress or strain sweep, frequency sweep, and then temperature sweep experiments, things like that for your samples. So, this is one of the paper we published on structure functional and rheological characterization, where you can know little more about the both the linear and non-linear viscoelasticity measurements. Small amplitude oscillatory shear, that's what the linear viscoelastic regions. You can also look at the non-linear viscoelastic region, description of method, how to conduct those type of tests. So when you are ready to do read about that, this is probably important information. You may want to read it so that you can understand a lot better about the non-linear viscoelasticity test and how to do those kind of measurement. Any questions? Anybody have a last minute question? Okay. This concludes our in-class discussion. Tomorrow we are going to come back to lab at 9 o'clock. I will be there and I will be doing some demonstrations. So if there is anything you want to learn during the practical demonstration tomorrow, please bring me the questions so we can discuss about in person, in close contact. Not like this, right? So at least we have some more opportunity to interact. And then you will all get all the information I shared the last 5 days or last 4 days, all the PowerPoint presentation and then e-books and then reference material also. You have my email address, so feel free to contact me if I can be of any help to you. So thank you all. Nice meeting you. See you tomorrow. Thank you.